Hello students, let us start our new session of chapter number 9, Mechanical Properties of Solids. Elastic moduling. Here if we are taking the ratio of stress and strain in the proportional region which obey the Hooke's law, that within that region the ratio of stress and strain is known as modulus of elasticity. So let us go through this part of that is a Young's module, in which if we apply the tensile or compressive stress, then the magnitude of strain is produced in a body which remains same. So if we are taking the ratio of stress, tensile or compressing, to its generated strain, which is a longitudinal strain, which is that ratio is known as Young's modulus, in which is denoted as a Y. So Y equal to sigma by epsilon 0. Sigma defines stress, epsilon defines strain. And we know that stress is nothing but applied force per area, and longitudinal strain is nothing but change in a length of that original length. So let us substitute both the values of stress and strain, and we able to get Y, Young's module equal to F into L divided by A into delta L. So here unit of Young module is the same as stress, because L by delta L, it's a unit will be cancelled out to each other. So that would be force by area, it is a Newton per meter square or Pascal, and its dimensional formula is again remains same, meter length inverse T raised to minus 2. Here in this table, number of substances are given, in which based on its density Young's module is given, based on ultimate strength, and its yield strength is also given based on the stress strain graph. So here we can observe that for metal the Young's module is very large. These materials are require a larger force to produce a very small change. So here we can see that to change or to increase its length of a thin steel wire by 0.1 centimeter square cross sectional area by 0.1%, so that is required around 2000 Newton force. So the force here is required to produce the same strain in aluminium copper wire having the same cross sectional area. So here we can see that it required 690 Newton, 900 Newton or 1100 Newton force. So in the comparison of steel, aluminium, brass and copper, we can say that steel is more elastic than copper, brass and aluminium, and that's why steel material is used where the heavy duty machines we need to design or any structural design we need to form. Instead of that, if we compare wood, bone, glass, these materials are having a very small Young's module. It means it requires less stress to deform. Let us go through the example regarding the same. A structured steel rod has a radius of 10 millimeter and a length of 1 meter. 100 kilonewton force stretches it along its length. Calculate stress, elongation and strain on the rod. Young's modulus of structural steel is 2 into 10 raised to 11 Newton per meter square is given. So here, as you can see, the rod is held by a clamp at one end and the force is applied onto the other end. So the parallel to the length of the rod. So stress applied generated on a rod, that is a force per area, that is F by A equal to F by pi r square. Force is given 100 kilonewton, pi that is a 3.14, r the radius is given 10 millimeter. By substituting all the values, we are able to calculate stress, that is 3.18 into 10 raised to 8 Newton per meter square. Now we need to calculate elongation. Elongation, it means we can say that change in length, that we need to calculate delta L. So we know the Young's modulus Y, that would be equal to stress by strain, that is F by A divided by delta L by L. From that equation, let us make the subject of formula delta L to calculate the elongation. So that equation would be like delta L equal to F by A into L by Y. And Young's modulus is already given in the example, that is 2 into 10 raised to 11 Newton per meter square, which is Y. So now we are having all the values. F, A, L is already given, that is a 1 meter, and Y is already given. So substitute all the values and we are able to get delta L equal to 1.59 millimeter. Now the third portion we need to calculate, that is a strain. Strain that would be equal to delta L by L. Now from the above point we are able to get the value delta L, and L is already given. So by substituting that values of delta L and L, we are able to get strain, which is 0.16%. Let us go through the another example. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both of diameter 3 millimeter, are connected end to end. When stretched by a load, the net elongation is found to be 0.7 millimeter. So obtain the applied load. So here copper and steel wires over which the tensile stress is applied, because they both are having the same tensile equal to the load. So onto the same cross-sectional area as given in the example. So we are having that equation, Young's modulus equal to stress by strain. We need to calculate stress. So stress equal to strain into Young's modulus. Stress, that is a force by area or the load by area, Young's modulus YC, into change in length, that is a strain, by applied L for the copper. That would be equal to, for steel, that is Ys into delta Ls by delta S. So we are equating the stress with the Young modulus and strain of copper, that would be equal to strain generated in steel. So here let us, as we want to calculate its elongation, let us make the subject of formula delta Lc by delta Ls. That would be equal to Ys by Yc into Lc by Ls. Lc is given 2.2 meter, Ls is given 1.6 meter. In Young's modulus, we can refer from the table that copper is Young's modulus of copper is 1.1 into 10 raised to 11 Newton per meter square, and Young's modulus of steel, that is 2 into 10 raised to 11 Newton per meter square. By substituting that values of Young's modulus and length of copper and steel, we are able to get that ratio is 2.5. So total elongation is already given, that is a 0.7 millimeter, right? So that is a delta C, delta Lc plus delta Ls, that would be equal to 0.7 millimeter. So we are having two equations, delta LC by delta LS equal to 2.5 and delta LC plus delta LS equal to 0.7 millimeter. Two unknowns, two equations. By solving this both the equations, we able to get delta LC equal to 5 into 10 raised to 4 meter and delta LS equal to 2 into 10 raised to minus 4 meter. So now substitute that values in the force equation, that is F by A equal to YC into delta LC by LC, or in the form of steel. Any of the equations, substitute the values and we able to get the applied force W equal to 1.8 into 10 raised to 2 Newton. Another example, in a human pyramids, in a circus, the entire weight of the balance group is supported by the legs of a performer who is lying on his back, as it is visible in the diagram. The combined mass of all the persons performing the act and the tables, pellicles, etc. involving is 280 kg. The mass of the performer lying on his back at the bottom of the pyramid is 60 kg. Each thigh bone of this performer has a length of 50 cm and an effective radius of 2 cm. Determine the amount by which each thigh bone gets compressed under the extra load. So here we need to calculate as we are having total mass of all the performers, tables and pellicules are given 280 kilograms. Mass of the performer is given 60 kilogram. Mass of the supported by legs of the performer at the bottom. So let us take the difference of total mass minus mass of performer, that is 280 minus 60, that would be 220 kilogram. So the weight of this supported mass, that is a 220 kilogram weight, let us convert it into the terms of force. So let us multiply with the 9.8 Newton. So 220 kilogram weight, that would be equal to 220 into 9.8 Newton. That is based on its MA, F equal to MA. So M is 220 kilogram, A, that is we are taking as acceleration due to gravity 9.8. So we are here, the weight of this supported mass we are having 2156 Newton. Weight supported by each thigh bone of the performer, that would be half of that total weight, that is half of 2156 Newton. That would be equal to 1078 Newton. Now from the table we are having the modulus of bone 9.4 into 10 raised to 9 Newton per meter square. The length of the thigh bone is given 0.5 meter and the radius of thigh bone is given 2 centimeter. So cross sectional area of thigh bone A is pi r square, which is 1.26 into 10 raised to minus 3 meter square. So compression of thigh bone delta L based on the Young's modulus Y equal to F by A divided by delta L by L. From that make the subject of formula delta L. Now we are having force F, that is 1078 Newton. L of the bone is thigh bone is given 0.5 meter. Young's modulus of bone we are having 9.4 into 10 raised to 9 Newton per meter square, and area we have calculated based on its radius 1.26 into 10 raised to minus 3. While substituting all the values we are able to get a delta L, that would be equal to 4.55 into 10 raised to minus 5 meter, or if we convert into the centimeter, that would be 4.55 into 10 raised to minus 3 centimeter. which is a very small changes occur, the fractional decrease in the thigh bond delta L by L, that is a 0.0091% occur, which is not visible or not can be experienced. Am I clear? Here we are going to end this session. Hope you understood. Thank you.